what exactly in detail about step down chopper or buck converter. Then I started what exactly step up chopper or boost converter, and I given what is analysis in continuous mode, what is analysis in discontinuous mode also I discussed. Okay. Now we continue with that topic only, that is boost converter concept. Here I want to give some mathematical analysis of boost converter under practical condition. Here practical conditions means whatever the concept I discussed in the boost converter, I am not consider any internal resistance of inductor. We are not considering any internal resistance of inductor. But practically every inductor offers some resistance also. If you consider the internal resistance of inductor, then what is the expression for average output voltage, that I want to discuss. Okay. That means here we are considering the resistance of inductor now. That's why that is a practical case. Okay. We continue with that. Write down, that is average output voltage of boost converter, that is boost regulator, as a function of internal resistance of inductance. You write average output voltage of boost regulator as a function of internal resistance of inductance. Internal resistance of inductance. This is practical case. This is under practical condition. Practical conditions. Average output voltage of boost regulator as a function of internal resistance of inductance. Now can you draw the boost converter? Yes, already given this circuit, boost converter, but if you consider the resistance also. This is inductance. Let the resistance of inductance is small r. Internal resistance of inductance is small r. This is switch arrangement. Switch or chopper. Parallelly draw the circuit. This is diode. And this is capacitor, filter capacitor. Let us assume that it is a resistive load. Okay. Voltage across the load is V0. Current through the load is I0. Current through the capacitor is IC. Then this is diode. Let the inductor current is IL. This is switch or chopper. You can take either chopper or switch. Then this is VDC, where small r is internal resistance of inductor. Internal resistance of inductor. Internal resistance of inductor, where capital R is load resistance. Okay, load resistance. One operation is nothing but a one on and one off. Now by controlling this circuit in on and off, then we want to find what is expression for average output voltage by using same concept what I discussed, volt second balance and ampere seconds balance. Okay, first chopper is on, chopper or switch is on. Then what about the diode? Diode is under off state. Then what is the equivalent circuit, you tell me? This is VDC, DC voltage, and this is inductance. These are internal resistance of inductance, small r. Chopper or switch is on. This is equivalent circuit. Diode is off state. This is capacitor, and this is load resistance. Capital R is load resistance. That this is I0, this is IC, positive negative V0. Okay. Okay. This is equivalent circuit. Then apply KVL and KCL. The voltage across the inductor is VL. Let voltage across the resistor also there. Voltage across the resistor is VR, or you take VR. Then what is KVL, you tell me? Then according to KVL, what you write? VL plus, this is VR. VR is written as, let the current in the inductor is IL. This is IL. That is IL into small r is equal to VDC. Then from this, what is VL equal to? VDC minus IL into small r. Applying KVL here. Okay, VL equal to VDC minus IL into small r. Clear? Then can you apply KCL? What is KCL, you tell me? Yes. IC equal to minus I0. IC plus I0 equal to 0. IC equal to minus I0. This is the case in the chopper is on. If the chopper is off, chopper is off. Chopper is off means which device is on? Diode is on. Can you draw the equivalent circuit? Chopper is off, diode is on. This is VDC. Voltage across the inductor is VL. And this is IL. Internal resistance of inductor is small r. This diode is on state. Switch is off state. Okay. Then this is the capacitor. This IC. The load is resistive. I0. Voltage across the resistance is V0. Okay. Then apply KVL. What is the KVL, you tell me? VL plus IL into small r plus V0 equal to VDC. Then from this, what is VL equal to VDC minus V0 into V0 minus IL into small r. This is during off state. What is KCL, you tell me? KCL is, this current is IL. Then what is IL equal to? IC plus I0. Then what is IC equal to? IL minus I naught. Correct. IC plus I naught. Then IC equal to IL minus I naught. This is during off state. This is during on state. Then to derive the average output voltage. To derive the average output voltage of boost regulator. Then you go for volt second balance, ampere second balance. The first one is apply volt second balance according to volt second balance. Can you tell me according to volt second balance? VL on into T on plus voltage across the inductor in off state into T off is equal to 0. Is correct? Yeah. What is voltage across the inductor during on state? This one. VDC minus IL into R into T on plus what is the voltage across the inductor in off state? VDC minus V naught minus IL into R into T off is equal to 0. So okay. Then you simplify this one. What do you get? Tell me. If I am simplifying this one. Yes. This is VDC minus IL into R. VDC minus IL into R is common. VDC minus IL into R is common. Okay. Then what we get? T on plus T off. T on plus T off. In this term, VDC minus IL into R is common. Here T off, here T on. This equal to this minus V naught into T off term, you bring this side. This V naught into T off. Is correct? Yeah. Shall you write like this? VDC minus IL into R. IL into R. T on plus T off is T. What is V naught, you tell me? V naught into, how to write T off? 1 minus D into T. Okay, this T cancel. Here, then from this, you want to get the expression for which one? You want to get the expression for V naught. VDC minus IL into R is equal to V naught into 1 minus D. From this, VDC equal to IL into R plus V naught into 1 minus D. Let this is equation 1. This I written according to volt second balance. Okay. Then what is the current second balance, you tell me? According to current ampere second balance. Go for ampere second balance. Then what is the ampere second balance, you tell me? According to ampere second balance, how you can write? IC on into T on plus IC off into T off is equal to 0. What is the current in on state? Minus I naught. That is minus I naught into T on plus what is off state current? IL minus I naught into T off is equal to 0. Shall you write like this? I naught into T on is dt is equal to, how to write? IL minus I naught into T off is 1 minus D into T. T cancel. Then d I naught equal to, that is IL minus IL into 1 minus D minus I naught into 1 minus D. Bring this 1 I naught is common, D plus 1 minus D is equal to IL into 1 minus D. Then from this, what is IL equal to? I naught by 1 minus D. This average load, average inductor current. IL equal to I naught by 1 minus D. This you substitute, let this is equation 2. Substitute equation 2 in equation 1. Why all this we are doing? To get the expression for average output voltage. Do this. Substitute equation 2 in equation 1. Substitute. Okay. Substitute equation 2 in equation 1. In equation 1. You tell me what you can get. VDC equal to, what is IL? I naught by 1 minus D into R plus V naught into 1 minus D. V naught into 1 minus D. How to write I naught equal to V naught by R? Then VDC equal to, shall you write like this? V naught by R into 1 minus D into small r plus V naught into 1 minus D. Clear? Then VDC equal to, tell me, small r, V naught is common. Shall you write like this? Small r by capital R plus 1 minus D whole square by 1 minus D. Then from this, what is V naught expression we get? V naught equal to VDC into 1 minus D by what you can get. Shall you write like this from this? V naught equal to VDC into 1 minus D by small r plus capital R plus 1 minus D whole square. This is expression for average output voltage as a function of internal resistance of inductor. V naught equal to VDC into 1 minus D by small r by capital R plus 1 minus D whole square. This is the expression for average output voltage as a function of internal resistance of inductor. In this, if small r equal to 0, then you can get 1 minus D cancel, VDC by 1 minus D. Same that of without any internal resistance of inductor, whatever the expression you derive, that you can get again. Okay, that's the only difference. If small r is 0, you can get the same formula, what you derived in the without any resistance. But if you consider the resistance, this is the expression for average output voltage. Clear? No doubt. Quick. Yes. Now from this, we want to make some observations that is important for compute. That you will see. Now you tell me, what is the expression for average output voltage we are getting as a function of internal resistance of inductor? V naught equal to VDC into 1 minus D by this. What is V naught we are getting? This is V naught equal to VDC into 1 minus D by small r by capital R plus 1 minus D whole square. This is the expression for average output voltage we are getting. Okay, but we know that without small r, what is V naught equal to VDC by 1 minus D. This is practical case. In this, if D equal to 0, if duty cycle is 0, what is V naught, you tell me? We can get some minimum value. D equal to 0 you substitute, D equal to 0 you can substitute here. Then what is V naught equal to capital R by small r into VDC. If D equal to 0, this is correct. Sorry, if D equal to 0, then what you can get? If D equal to 0 you substitute here, this is 1 you can get. Then VDC by capital R by small r by capital R plus 1 you can get for D equal to 0. Then for D equal to 1, what is V naught you get? V naught equal to D equal to 1. This is 0. V naught equal to 0. For duty cycle equal to 1, V naught equal to 0. Then in this case, for D equal to 0, what is V naught equal to VDC? For D equal to 1, what is V naught equal to infinity? That means ideally take V naught equal to VDC you can get, but exactly VDC you don't get in the practical case. This much of voltage we can get. For duty cycle equal to 1, in the case of practical condition V naught is 0. But in the ideal case V naught is infinity. This is not possible. Practically this is correct. Even I told in the previous session also. For D equal to 1, don't take infinity. Practically it is a 0 volts. This is the proof. Practically V naught equal to 0. D equal to 1. What is the reason? Yes, sir. If you take D equal to 1, capacitor is discharging. Capacitor is discharging means the voltage across the capacitor is 0. The voltage across that means whatever the capacitor connected across the load, it is short circuited. Then the voltage across the load equal to 0. But always inductor is storing. Then it is a unstable operation. But this is the proof under D equal to 1 condition. For practical case, what is the V naught? 0. Then by considering these two conditions, this is with small r, this is without small r. Then if you draw the characteristics, this is average output voltage here, this is duty cycle. Ideally for D equal to 0, we are getting some minimum voltage. For D equal to 0, we are getting VDC. From this, output voltage is increasing. For D equal to 1, it is infinity. Okay. But what about the practical case? For D equal to 1, we are not getting VDC. Below this we are getting. Then we are getting output voltage waveform is like this. This is D max. This is the duty cycle at maximum output voltage. When I taken it reaches to maximum value, then it will goes to 0 voltage. For D equal to 1, practical case D equal to 1. This is practical case. This is ideal case. Ideally at d equal to 1 it is a infinity. Okay. Then this is the characteristics we are getting if you draw the d versus v naught characteristics. Then this is v naught max. This is v naught max. There is a maximum average output voltage in the practical case. Then again duty cycle is increasing, average output voltage is reducing. Duty cycle is increasing, output voltage is reducing. Then this is unstable operation. Unstable operation. Average output voltage increasing. If duty cycle is increasing, average output voltage is reducing. At d equal to 1, average output voltage equal to 0. This is unstable operation. Now you want to find at what value of duty cycle the average output voltage is maximum. That means find the condition for practically where the average output voltage is maximum. That means to find duty cycle, at which average output voltage is maximum. At which average output voltage is maximum. Average output voltage is maximum. Then dV naught by dDd equal to 0. Differentiate with respect to duty cycle and equate to 0. Then differentiation of V naught with respect to duty cycle. What this one? VDC into 1 minus d by small r by capital R plus 1 minus d whole square. Then this equate to 0. Then from this we can get duty cycle equal, that you do. Differentiate and equate to 0. Then you can get the expression for duty cycle equal to 1 minus square root of small r by capital R. This duty cycle is nothing but a d max. This is the duty cycle at maximum average output voltage. Duty cycle at maximum average output voltage. What is the duty cycle at maximum average output voltage? But you know that in a boost converter, without considering the internal resistance of inductor, where the average output voltage is maximum at d equal to 1. That equal to, you substitute small r is 0, then you can get d equal to 1. That's why it is the duty cycle at maximum average. At this duty cycle, output voltage is maximum. We know the condition for maximum. We know the condition where the average output voltage is maximum. But you want expression for maximum average output voltage, na? Then how to get expression for maximum average output voltage? Yes. Substitute this condition in the actual voltage expression, then we can get the what is the value of maximum average output voltage. Then substitute d max in V naught. Then we can get V naught max. Then what is the maximum average output voltage is? VDC by 2 square root of capital R by small r. This is the maximum average output voltage. This is the maximum average output voltage. This you remember. This important formula and this. Sir, how you are getting this expression, sir? Means this you substitute here, then you get this expression. V naught max equal to VDC by 2 into square root of capital R by small r. Capital R is load resistance, small r is internal resistance of inductor. Okay, this about what exactly? The analysis of boost converter by considering the internal resistance of inductor. Clear? Okay, concentrate. Note down quick. For quick reference, I want to give summary of boost converter, that is boost regulator. That is all the formulas I want to list out here. Completed. Practically we don't get VDC, less than VDC we can get. This is a practical case. Less than VDC we can get, but this is the ideal case. Okay, what is the value of duty cycle at which average output voltage is maximum, that you derived now? 1 minus square root of small r by capital R. What is this V naught max? V naught max equal to VDC by 2 into square root of capital R by small r. Okay, let's concentrate. So you can get like this. This is ideal, this is practical. Now let's concentrate. Summary of for boost regulator or step up chopper. Summary for boost regulator. Boost regulator or step up chopper. Step up chopper. Yes, tell me. One is, what is the average output voltage V naught equal to? The average output voltage V naught equal to VDC by 1 minus T. This is continuous mode of operation. Once you know the V naught, how to write I naught equal to V naught by R, then I naught equal to average load current V naught minus E by R. This is for which load? R comma RL load. This is which load? RE load. Okay, next. For the average inductor current we are getting IL average equal to that is IL equal to I naught by 1 minus T. All these formulas I already derived. The summary I am giving. Okay. Next. IL average equal to I naught by 1 minus T. But it is not equal to I naught. What I discussed in the case of buck converter. Third one. What the average source current? Average source current equal to I naught by 1 minus T. Next. Fourth one. What is the peak to peak ripple current we are getting? Peak to peak inductor ripple current delta IL equal to dVdC by FL. This formula I derived, and delta IL is maximum at D equal to 1. Or the fifth formula I derived, S. What is IL max? IL max equal to IL plus delta IL by 2. What is IL min? IL minima equal to IL minus delta IL by 2, where IL is I naught by 1 minus D. Sixth one. What is the average switch current? average switch current equal to di naught, or the RMS switch current root di naught. What is the peak value of switch current? IL max. Okay. What is the peak value of switch voltage? Peak value of switch voltage equal to VL plus VDC. This equal to V naught. This is with respect to switch I derived. Next. Seventh one. What is average value of diode current? ID average I naught into 1 minus D. That is not I naught. This is IL into 1 minus D. Average value of diode current. That is 1 minus D into IL. What is the RMS value of diode current? Square root of 1 minus D into IL. Okay, this formula is derived. Then eighth one. What is the peak to peak capacitor ripple voltage? Di naught by Fc. Ninth one. What is the critical inductance? R into D into 1 minus D whole square by 2F. This formula I derived now. R into D into 1 minus D whole square by 2F. What is the critical capacitance? Cc equal to D by 2Fr. Okay. Under discontinuous mode, in discontinuous mode, what is the average output voltage of discontinuous mode? That is average output voltage of discontinuous mode is VDC by average output voltage of discontinuous mode is VDC by, that is beta into beta by beta minus D into VDC. This formula I derived. Okay. Then what is IL max equal to delta IL? V naught in discontinuous mode is greater than V naught in continuous mode. Here it is maximum at delta Vc, maximum at D equal to 1. Then what is delta Vc max, you tell me? I naught by Fc. It is maximum at D equal to 1. What is delta IL max, you tell me? VDC by FL. VDC by FL. Okay. This is under discontinuous mode. Next. Practically, if internal resistance of inductance is considered, internal resistance of inductance, if internal resistance of inductance small r is considered, can you tell what is V naught equal to? VDC into 1 minus D by small r by capital R plus 1 minus D whole square. Then 13 one. Practically in boost converter, for D equal to 1, what is V naught? 0. For D equal to 1, V naught equal to 0. Then V naught is at maximum average output voltage. At maximum average output voltage. The duty cycle D max equal to 1 minus square root of small r by capital R. Practically, what is V naught max? V naught max equal to VDC by 2 into square root of capital R by small r. All this is summary formulas. VDC by 2 into square root of capital R by small r. Okay. These are the different formulas we derived in the case of boost regulator or step up chopper. Okay, list out all these. Quick. Okay, clear? And I want to write one note here that you concentrate. You know that in buck regulator, what is Is equal to di naught? What is V naught equal to d times of VDC? That is average source current equal to di naught, V naught equal to d times of VDC. It's correct. In the case of buck regulator, for the average source current that you derived. Okay. That means what is I naught equal to Is, I naught equal to Is by d. What is V naught equal to dVDC? If duty cycle is increases, I naught reduces, V naught increases. That means if voltage increases, current reduces. Voltage increases, current reduces. It's just like if voltage increases, current is reduces. In the case of transformer, this observation you know. Voltage ratio and current ratio is inversely proportional in the case of transformer. Understood? That's why here also same happening. If voltage is increasing, current is reduces. Understood? But here in buck regulator always voltage is step down na. Understood? It is similar to that of step down transformer. That's why a buck regulator is equivalent to step down transformer. Therefore, a buck regulator equivalent to step down transformer. Then what about in boost regulator? In boost regulator means in step up chopper. What is Is equal to I naught by 1 minus d? What is V naught equal to VDC by 1 minus d? That is I naught equal to Is into 1 minus d. V naught equal to VDC by 1 minus d. If duty cycle is increases, V naught equal to VDC by 1 minus d. If duty cycle is increases means, for example, for d equal to 0.1, what is I naught equal to 0.9 Is? What is V naught equal to? 10 by 9 times of VDC. That means if duty cycle is increases, what about I naught? Reduces. What about V naught? Increases. Okay. That's why it is also similar to transformer action. If voltage is increases, current is reduces. The voltage and current ratios in transformer is inversely proportional. That you know, E2 by E1 equal to I1 by I2 equal to N2 by N1. This is a relation. That means if E2 is increases, I2 is reduces. If V1 is increases, I1 is reduces. That is the meaning. Voltage and current ratios are inversely proportional. In the case of here also same happening. If the voltage is increasing, current is reducing. That's why. But in the case of boost regulator, always output voltage is increases now. We can step up the voltage now. That's the reason why a boost regulator is equivalent to which one? Step up transformer. Equivalent to step up transformer. Yes. Therefore, final observation is a DC to DC converters are equivalent to DC transformer. Equivalent to DC transformer. We don't have any DC transformers, but its action is similar to that of transformer. But here, which voltage we are step up and step down? DC voltage. That's why DC to DC converters are called DC transformers. We don't have any DC transformer, but here we are step up or step down the DC voltages by using the DC to DC converter. That's why it is equivalent to DC transformers. Okay, this about in detail analysis of what exactly boost regulator. With this, in the previous sessions, I explained about what exactly buck regulator and what is the summary of buck regulator, and what is the boost regulator and what is the summary of boost regulator. With this, buck regulator and boost regulator is completed. That is, step down chopper and step up chopper is completed. The another very important converter for any competitive point of view, that is up down chopper or buck boost regulator. In the next session, we will continue with up down.